found on the SANS registration page. And with that, I'd like to turn the webcast over to Jim.
Thanks, Carol. As Carol said, I am a SANS instructor. I teach Forensics 610, reverse engineering malware. I also am a handler.
Excuse me, if you pause screen share, the slides won't be moving, but I'm not sure if you did or not.
Yep. Thank you. Okay. Yeah, as I said, I am a SANS instructor. I teach Forensics 610, reverse engineering malware. I'm also a handler at the SANS Internet Storm Center. In my day job at AT&T, I'm a malware analyst and do forensics. A little bit about the talk today. Most of the tools and all of the techniques that we're going to talk about, we cover in Forensics 610. But I want to talk about a few tools that we don't talk about in 610. And though I have slides here, most of this I'll probably actually demo because I think it makes more sense to see it in action. So a brief outline of the webinar, though. I'm going to give a little background on what Shellcode is, why we care, what we want to do with it. Then I want to show you the tools and the techniques, and hopefully we'll have some time for Q&A at the end if anybody's got any particular questions. So with that, let me dive right in. What is Shellcode and why do we care about it? If you saw my bio when you registered for the webinar, you know I've been doing IT stuff for a long time, been doing security stuff for a long time, and I first started hearing about Shellcode 25 years ago-ish. When we talk about Shellcode, though, what we're talking about is just some blob of binary machine code, executable code. And the goal is that we want to get some program running on the system to jump to this blob of executable code and execute it on our behalf. So as I said, I first started hearing about it about 25 years ago, probably. And in that case, it was in the context of folks trying to exploit, buffer overflows, stack overflows, heap overflows. And so the exploit developer, the attacker, was shoving this shellcode out into memory someplace and then trying to take advantage of some vulnerability in the code that they were trying to exploit to get the code to jump to, to get the program to jump to their shellcode wherever they had managed to place it in memory. These days, though, I'm seeing it quite a bit as one of the stages that malware authors are using, rather than just have one executable that they drop on the file system. They're often doing this in stages. They'll have a first stage that will drop or download a second stage that will potentially deobfuscate something and execute a third stage and a fourth stage and a fifth stage. And in the malware author's case, most often I'm seeing this as this blob of binary code that they attempt to inject into a running process via ordinary code injection techniques or process hollowing, but they'll create a thread someplace, put this shellcode in there, and then fire up a thread. So in those cases, the malware author is creating this shellcode not just to randomly place it in memory. So often with exploits, you'll see some big no-op sled. Sometimes with malware shellcode, there's no no-op sled or a very short no-op sled. No-op sled is just a bunch of no-op instructions placed in front of the shellcode so that the exploit developer doesn't have to be exactly precise in figuring out where they're going to get the exploited program to start executing. It'll hit one of the no-ops and then slide down till it finally reaches the beginning of the shellcode. The other point that I do want to make here, I'm going to focus on shellcode for Windows because that's the shellcode that I deal with most often. The concepts in general work in other operating systems. We don't necessarily have all of the tools that I'm going to show for other OSs, but it would be possible to create them. So with that, what do we want to do with this shellcode? Well, we can do all of the same kinds of things that we do normally in malware analysis. We can look at static properties of it. Granted, we're talking about a small piece of code. It's not a full-blown executable, so it's not going to have, PE headers and MZ headers and all of that. But there are still some useful static properties that we can look at. We can analyze it behaviorally. We can run it or emulate the execution and see what it does. Again, as we emphasize in Forensic 610, you generally want to do this on a lab system. You don't want to do this on your work laptop or desktop. That could be a career limiting move. But in your lab environment, you can emulate the execution in some cases, or just go ahead and execute it and use all of the normal behavioral analysis tools that we would use in analyzing any other malware. We can watch to see what registry keys it plays with. Does it try to do network activity, reach out to some website and download an additional phase? We can also use our code analysis techniques. We can load it up into a disassembler, and we can try to examine it, code the lines of code, the executable instructions, look at it instruction by instruction. I'll be honest, I don't often do that in any depth. I will usually basically glance at it. I have actually recently seen a couple of blog posts, and if you follow me on Twitter, I will post links to those shortly. There were a couple of really good blog posts, and I don't remember off the top of my head who did them now, of some folks who went into some significant depth on statically analyzing shellcode and figuring out what all was going on. I'll be honest, as I said, most of the time when I'm looking at shellcode, as part of a malware incident, I'm more interested in what is it going to do next, because most of the time it will be downloading or dropping another payload and executing that. So I'm interested in what happens next. And as part of the code analysis, in addition to looking at it statically, we could also throw it in a debugger and look at it in the debugger and examine it that way, single step through, and again, find out what it's calling. Is it downloading a next stage, whatever. So I'll look at some of the tools that we can use to do each of these steps, and that's going to be the bulk of the remainder of this webinar. As I said, I'm not going to spend a whole lot of time in the slides, but I do want to give you some examples of things you can do. Statically, one of the things we often do with malware is we'll run the Linux file command on it. When we're talking about shellcode, usually that's not going to tell us much. It's just going to say it's data. If it says it's ASCII with long lines, then maybe we haven't quite gotten to the executable version of the shellcode yet. One of the other things that we can do with it is we can run the strings command on it. I mean, that's one of the first things that I do with any malware. And in the case of the shellcode, sometimes we'll find usable strings. In the case of the shellcode that we're going to use for the majority of the demos coming up here in a minute, we do in fact have a user agent string and what looks like an IP address. This can be very useful for us. And one of the other things that I will often do is I will throw it into some sort of a hex viewer. On Linux, you can use XXD. I happen to like B more, but the format is pretty standard for most of these hex viewers. In the first column, you've got an address, offset, how far into the shellcode we're looking. Then the middle section will be the hex bytes that are represented there, and then the right-hand column will be the ASCII representation. And sometimes you can see interesting things, just by looking at it in a hex viewer. And so let's go ahead and jump over to my virtual machines here. We can show some of this stuff in use. And so the particular shellcode sample that I'm going to concentrate on for the first part of this was one that was actually found in the wild. My friend and fellow Storm Center handler, Xavier Martins, actually did a SANS handler diary on this sample. I believe it was as part of a document file. Had several stages were obfuscated, and one stage had a PowerShell script that in it had this Base64 blob that turned out to be the shellcode that it wanted to execute. And so just taken from his Storm Center handler diary, I'm going to go back and in the handler diary, he found this chunk of Base64 encoded stuff. And what we're going to do here is we're going to use a couple built-in commands on Linux, echo and the Base64 command. And we're going to take this Base64 stuff and turn it into the binary shellcode that we're going to look at. And so then I can run the file command on this. And as I said, it shows it being data. You can run the strings on it. And again, we see what looks like an IP address. We see what looks like a user agent string. Not seeing much else. See a win, or win I and net up here. So if we look at this in BMore, or as I said, you can use XXD or whatever your favorite hex editor is, ghex editor, whatever. And we look, there's not all that much to it, but you know, as I showed in the strings, we've got this string net, the string Winnie, W-I-N-I. And if you notice in the string section here, the W-I-N-I and the net are preceded with the lowercase h. And that's one of the things that I do actually look for. The lowercase h is represented in hex as 68. Well, 68 is the hex value for the opcode for a push instruction, pushing an immediate value onto the stack. So what it looks like here is we're pushing WINI and NET onto the stack in reverse order. So it looks like we're pushing the name of a DLL, probably going to be used by a load library call. And as I said, we've got a user agent string, got what looks like an IP address. But I'm not sure that I can get a whole lot more out of just looking at this with the Hex Viewer. So we'll wrap up the static properties here with this. Let me switch back to the slides. So once we've covered what we can do with looking at the static properties, next thing we want to do is look at it behaviorally. And one really nice tool for this is called SCDebug. It's been around for quite a while, and you can find it at this URL. Well, this first URL, the 4610.com/SCDebug, is a pointer to a blog post that explains how to actually run it. SCDebug-download will take you to the GitHub page where you can download the version of it that is still being somewhat maintained. I think the last check-in I saw there was like 7 months ago. Now, most of the time in Forensic 610, we use the Windows GUI version, but I did want to show that we can actually run it's also a command line tool, which can run on Windows, or I like to run it on Linux. It runs just fine under Wine. And what you see here is it's 343 bytes of shellcode, and SCDebug will emulate the instructions of the shellcode. So it isn't actually running the code, it isn't actually modifying the file system or registries or actually making the outbound connections, but it will emulate these instructions and show you what the code would have done if you had actually run it. And this is really nice. As we can see in here, the load library WinINet, we saw that being pushed onto the stack in 2 pieces there. Then apparently it figures out where the internet open call is. It's an internet connect to that IP address that we saw. So that IP address was in fact significant. It's trying to do a connection on port 443. One of the other strings in there was this path. So the URL that it's trying to get is it's 31.220.45.151/VDAA. And then it's doing an internet send request and then virtual alloc. So it's allocating space where it's going to save whatever it reads back probably, and then doing an internet read file and waiting for the web server to send something back to it. Okay, this is really useful information for me. Now I've got some potential IOCs, some indicators of compromise. But in fact, since it's emulating it, it's not actually going out to the internet to make this connection. So we're not seeing what it is that it downloads. Okay, that might be a problem. I might need to go out and make a connection to this site to download the next stage, the next payload that it's trying to download. So let's go ahead and let me show this to you as well. And I apologize for the slowness in switching between screens here. So, as I said, SCDebug runs quite nicely on Linux under Wine. You can see I downloaded from GitHub the version that is still being somewhat maintained. Now, there did used to be a Linux version. The Linux version has not been maintained for quite some time. The version that is still being somewhat maintained is just the Windows version using Visual Studio. So scdebug.exe, and if I just give the -F option for the file that contains the shellcode, and shellcode.malicious. Now, if I just run this straight, and many times this will show me something useful. In this case, though, it doesn't show me everything. By default, it will run for 2 million steps and then quit. And so apparently that wasn't enough for this piece of shellcode to do everything it needed to do. So if I add the -S option, I can use -1 to let it run however many steps it takes. In this case, I'm not going to do that because we saw that it's waiting for an incoming connection that it never gets. But I am going to execute it for 10 million steps. And so if we do that, then it gets further, it gets to the internet read file, and then it never gets its response, so then it quits. So, okay, very nice. Now I also showed you the slide that you can use the GUI version on Windows, and I have the same shellcode over here. If I just drop this on there. Now again, by default, if I just go ahead and click launch, it's only going to run it for 2 million steps. I can add additional arguments to make it run for 10 million just by adding that here and then clicking the checkbox. And so we see, get the same result doing it by the command line, from the command line, or from the GUI version. Now, the GUI version is probably the version that I use. Well, it is the version that I use most often in class. In real life, it's about 50-50. But if you've got a chunk of binary data that you believe there's some shellcode contained within, one of the options is you can have the SCDebug try to find the beginning of the shellcode yourself, or you can tell it where this starts. And these are options you can give on the command line too. So. Okay, but sometimes for whatever reason, SCDebug won't give you everything you need. Sometimes, rather than emulating, we really do need to go ahead and execute it and see what it really does when it runs. We've got a couple of tools that we can use to actually execute the shellcode. Now remember, shellcode is just this blob of machine language instructions, this blob of executable code. It is not a complete executable. So if we're going to run it, we need to use some tool that will either wrap this shellcode in an executable, in a PE file, create a PE header and all of that stuff, or have some other program that will run, that will at runtime read this in and execute it on the fly. So one of the tools that we use in the class is this shellcode to exe Python script, and you can find info on that here at the for610.com/shellcode.exe. And this will take a blob of shellcode and wrap it in basically an empty executable, shove the shellcode into it. Shellcode.exe, really nice tool, not being currently maintained, and sometimes there's some issues with getting it to run on newer operating systems. It's included in Remnix, and I believe that Lenny plans to continue to include it when he does the Remnix update, probably later this year. But I have found, oops, that went the wrong way. I have found another Windows batch file that will do essentially the same thing, shellcode to exe.bat. One of the, backing up just a second, one of the issues with shellcode to exe is the Python version, is that it only handles 32-bit shellcode. Now, granted, the vast majority of the shellcode that I have encountered in real malware investigations was 32-bit shellcode. But with 64-bit versions of Windows have been out for quite some time, and with Microsoft basically dropping 32-bit versions of the OS, I am starting to see more 64-bit shellcode. And one of the issues with the Python script is that it only handles 32-bit shellcode. And one of the things that I mentioned in class is it'd be nice if somebody wanted to take it on as a project to extend this to handle 64-bit shellcode. The shellcode.exe Windows batch script does in fact handle both 32 and 64-bit shellcode. You just have to tell it what it is that you're passing to it. So we can let me show you these real quick. So the Windows batch script version can be found on GitHub, and as I said, you tell it whether it's 32 or 64-bit shellcode. The copy of the shellcode I've got is up on my desktop. So, and I'll save the executable up there too. And you see this little error message. I don't know if that's a result of Git or whatever, but for some reason it's got these @ signs in front of the labels that at least this version of Windows doesn't care much for them. But now I've got this executable here that I can go ahead and run and use all of my normal behavioral analysis tools. I can use Process Monitor and Redshot and Wireshark and all of those tools, and I could just go ahead and run this. I'm not going to do it right now. I'll save the executing for a little bit later. And, so behaviorally can monitor and potentially see, what, excuse me. Sorry about that. Tickle in my throat. So we've turned it into an executable. We can go ahead and then execute it, observe it behaviorally, see what it does. Another thing that we can do with it to observe it behaviorally is we can use jump to it, which is a tool that we use quite a bit in Forensic 610. So on the desktop here, I can say jump to it, and shellcode.malicious, and then I have to give it the offset. Where is the shellcode located in this binary blob that I'm passing to it? In this case, the shellcode is all that's in there. It starts right at the beginning, so I give it an offset of 0. And I can let it run. Again, I could have fired up process monitor and Wireshark, whatever, and let it run. I'm gonna let's go ahead and kill it. Oh, did it die on? Did it quit? Oh, it did quit. Okay. One of the nice things about jump to it is that it creates this capture file, so I don't have to actually run Wireshark when I'm using jump to it. And yeah, because it got cut off. Well, I guess it got cut off in mid-packet, so we didn't get a good copy of it. But this would have, if I'd let it run a little longer before killing it, it would have shown a 3-way handshake, or an attempt to send packets. I don't have a web server accessible from here. So that's one of the nice features of jump to it, is that it does do the capture of the PCAP for you. Let's see. Now I mentioned that we can also attempt to do code analysis on it. I guess I got my slides a little bit out of order. Let me switch back to the slides for a second, and then there we go. Oops. So we could also load it into a debugger using either the executable that we created with shellcode.exe, batch script, or the Python script, either way. Or we can use jump to it in a slightly different fashion, get it to pause, and we can connect the debugger to that process. And then we could single step through using X64Debug or whatever your favorite debugger is of choice. Now, I want to point out these 2 documents here. A former Forensic 610 student, Nader Shalabi, created a tool that we'll look at in a little bit here for doing 64-bit shellcode. But he also has a couple of nice write-ups, one about using his tool and the Visual Studio debugger to do the debugging, and one about using a tool called Frieda, which actually I like and has a lot of potential. It intercepts the API calls, and so it can give you a lot of the same stuff that SCDebug did, while actually executing it, though. That's the difference between, whoops, I've got the wrong set of slides up here. This is what I really wanted to be showing you. So his little write-up on using Frieda, it shows you all the same kinds of things that SCDebug did. It will list all of the API calls and show you the parameters and so forth. The difference is that this is actually running it. So again, be very careful. Make sure you do this on a disconnected lab system. But you can also load the shellcode into your disassembler of choice, and look at it there. Dedra is, the new kid on the block and the one that's getting a lot of attention there. But you can use Redare or IDA, and you can examine the shellcode statically in one of these disassemblers. Now, one thing you should note is that most of the time when you load it into the disassembler, it's not going to look like this first time out. So if I take this shellcode and, well, let me go ahead and fire up Dedra. So if I drop the shellcode in here, first of all, when I'm dropping shellcode in here, I have to tell it what architecture, and so forth the shellcode represents. So since Dedra can handle a number of architectures and a number of sizes and endianness, I need to go down to x86, and this is 32-bit shellcode, and I usually just use Visual Studio. For shellcode, it probably doesn't matter a whole lot. So we load it in here, and Dedra imports it. Yeah, okay, it's 343 bytes. This doesn't tell me a whole lot. If I open this up then, though, and have Dedra analyze it, again, this is not a full-blown executable, so there isn't going to be much analysis. Yeah, we'll go ahead and analyze it, and I'm just going to take all of the defaults for the time being. And let me maximize this, and we'll see that it didn't take very long because Dedra couldn't find a whole lot going on here. But this doesn't look like assembly language. This is just each of the bytes listed individually here. If I right click and choose disassemble, now I've got assembly language stuff that I can look through here and try to analyze. As I said, personally, I don't do this a lot, but you should be aware that you can do it if that's interesting to you, or if you, for some reason, you need to do that. And I'm not going to save this for the time being, but I did want to show you that sometimes you need to explicitly tell the disassembler that this is code, and so it needs to disassemble it. Okay, so most of the tools that I've been showing you up to this point work on 32-bit shellcode, and that has been an issue. Until now, there haven't been a lot of tools that could handle 64-bit shellcode. That's where Nader Shalabi's Run Shell 64 tool comes in handy. Run Shell 64, like Jump to It, is an executable that will read in the shellcode at runtime and allow you to execute it or debug it. Should note that the disassemblers, though, can all handle 64-bit shellcode as is. So let me come back one final time to the VM. So I've got some 64-bit shellcode here. Actually, let's get Dedra back up and look at this in 64-bit first. So if I take 64-bit shellcode and drop it in here, again, I need to tell Dedra that it's x86, but it's 64-bit shellcode. Again, I choose Visual Studio, just that's my default. And if I look at the 64-bit code, yes, go ahead and analyze it. Yeah, just take the defaults again. Look down here in the lower right-hand corner. It's not going to take very long. Again, it didn't show me much of anything, so I right-click and disassemble. And now I've got 64-bit code here that I can try to examine and figure out what it's doing. No, I don't want to save that. Now let's close that for now. But the Nader's tool, the Run Shell 64, is a nice tool. I actually put a shortcut for it up here on the desktop. And you can run this. You can, it asks where is the shell code, so you can load the shell code. Now, one of the nice things and we use jump to it in the class for doing this, is this will, with 32-bit shellcode, is we can load shellcode into one of these tools, and then we can attach a debugger to it and single step through the code in the debugger and see what it's doing. That can be very useful. I like the insert breakpoint version. That's probably a personal thing. If you click run, it says breakpoint is set. So now I should run a debugger and attach to the running process. In this case, it's the run shell 64. And the attached breakpoint is reached. And then I run again. Click back here. Click OK. And now I can, and now I've reached by clicking this insert breakpoint checkbox, it puts the int3 instruction actually in there at the beginning of the shellcode. So now I can no-op this out. And now I can single step through the shellcode. And I can watch what happens in the registers or on the stack. And this can be very useful for examining shellcode. So we're almost out of time here. So let me see if we've got any questions. That's pretty much all I wanted to cover here. So we've looked at a couple of tools that we can use to do our standard malware analysis type activities, both the static properties, behavioral, and the code analysis. So what questions do we have? Caroline.
All right, thanks, Jim, for that great presentation. We do have a few questions ready for the Q&A. The first one I put into your questions window. It's got a lot of abbreviations and stuff, so I'm hoping you can read that one to the group. Okay. So if you expand your questions window, you should see that.
And I'm having trouble expanding.
If not, I'll read it to you. I think it says scale debugger works on x64 shellcode. If not, is there an x64 equivalent? Okay, yeah. I'm pretty sure that the version of libemu that SCDebug uses is only 32-bit. That's why I, for 64-bit, tend to use Nader's new tool and just debug it, or as I said, his use of Frieda to hook to intercept the API calls looks like an interesting technique. I haven't actually used it, but I do like his write-up there. So I'm not aware of a version of libemu that actually is 64-bit compatible, that understands 64-bit shellcode. So when I encounter 64-bit, I execute it rather than emulate it using the tools that I just talked about there. So either the shellcode.exe batch file or naders run Shell64.
All right, thank you. Will there be a Windows version of Remnux, R-E-M-N-U-X?
No, not exactly. I believe that the version of Remnux that Lenny is currently working on, hopefully will be out later this year. It will use salt stack to enable you to install the tools on. We're starting out on Ubuntu 18.04, but it should work just fine on 20.04 probably once that's released next month. And the next version, all of those tools probably will run just fine under the WSL2, the Windows subsystem for Linux, which allows you to essentially install Linux on your Windows system, on your Windows 10 system. So the Linux only tools actually should run under WSL2 later this year. But for right now, Remnux is a separate VM that is available. Remnux.org, I think, is where Lenny keeps that distro. But yeah, we'll hopefully later this year you'll be able to execute all of the tools that we right now run exclusively under Remnux. You should be able to run them under WSL2 later this year, hopefully.
All right, thank you. I think perhaps you may have addressed this, so feel free to pass on it. It says, I think, but shellcode 2.exe.bat and shellcode 2.exe.py can handle 32 ANS 64, right?
The Python script cannot, the batch script can. The Python script is 32-bit only.
All right, thanks. Someone asks, how do I determine offset?
Well, sometimes you just have to hunt around for it. We have a couple of examples that we use in Forensic 610 where we just look through it until we find a no-op sled, a bunch of 90 hex, 90, 90, 90 in hex, because 90 is the opcode for the no-op instruction. So sometimes you just have to visually look until you find it. Another technique that we talk about in the class is using Didier Stevens' XOR search tool to try to find a get EIP pattern, which Shellcode often needs to do to try to figure out where it's where it is loaded in memory, so that it can find any strings that are statically contained within the shellcode. So there are a couple of ways of finding it. Sometimes if I'm not sure exactly where the shellcode is in the binary blob, as I said, I'll use the switch and see if SCDebug can find it using its heuristics. But there's, sometimes it's trial and error. But there are a couple of heuristics that we talk about in class, and yeah.
All right, well, that's all we have for today. Thank you so much, Jim, for your great presentation, which helps bring this content to the SANS community.